In this video, we learn how to find the antiderivatives or evaluate trigonometric integrals. We know a lot of these already, actually. Some of the basic forms of our antiderivatives, right? Integral of sine is minus cosine. Integral of cosine is sine. We need those as building blocks for what we'll be working on in this section. But basically, we'll be looking at things like cosine x divided by square root of sine x and how to evaluate that integral, or something where I've got different powers of secant and tangent, or cosecant, cotangent, just different things all kind of working together. And a lot of this section will be based on taking advantage of our trig identities, okay? And I'm going to focus on this kind of top section here. The product to sum identities are useful, and we can find uses for them when evaluating integrals, but I want to basically just kind of put all of my attention into the Pythagorean identities and power reducing identities. Okay, so I'm going to go through some examples in this video, and then I'm going to highlight basically the guidelines, or kind of the decision-making process that I use to try to figure out how to evaluate some trig integral. So the first example I have here is I've got different powers of sine and cosine there. I've got sine to the third power and cosine to the fourth power. And I want to figure out what the antiderivative, what the integral of this thing is. Okay? So what I'm going to try to do is work with the powers to try to hopefully figure out how I can evaluate this integral. And really the first thing that we want to kind of try is, if u is sine x, then du is cosine x, right? We just try to do a substitution. We fall back to what we know, but we quickly see that just that substitution there isn't going to handle all of the cosines in my problem, right? So I would have just a cosine taken care of, but I've got three more than cosines to deal with. So what we try to do is pay attention to the powers here. I've got an odd power of sine. So what I'll do is I'll pull off a sine of x, okay? A lot of those identities on the previous slide give us, or make use of, an even power of sine or cosine. So I don't really want odd powers here. So what I'm going to do is I'm going to take a factor of sine of x away and see what I can do. So if I've pulled sine of x away here, what I'm kind of hoping for is that sine of x is going to take the place of like a du in a substitution. If I were to let u be cosine of x, I see that cosine to the fourth, that means I would have u to the fourth in my integral. All right, I would have u to the fourth, but then du would be minus sine of x, and I've got an extra sine of x there. So maybe that's a decent way to approach this. If u is cosine x, then du is minus sine x dx, and I see that I've got sine x dx right in my integral there. I just replace it with a minus du. So that cosine to the fourth power becomes u to the fourth. The sine x dx becomes a minus du, and I still have this sine squared left over. Okay? But sine squared, I can replace using one of the identities on the previous slide. Okay? So again, I can handle squared powers of sine or cosine pretty easily. What we do here is I have two choices. The first is my Pythagorean identity. The second on the previous slide was power reducing. Okay? And I'm going to use the Pythagorean identity here. I'm going to move around sine squared x plus cosine squared x is 1 to get that sine squared x is equal to 1 minus cosine squared, because I've already made a substitution where u is cosine of x. So I should then be able to just replace cosine squared x with a u squared. And I don't have any more sines or cosines in my integral. I end up with u to the fourth times 1 minus cosine squared x du. And I can't mix x's and u's. Like I said, I got to replace that cosine squared, but I can do that with u squared. So I've substituted completely. In fact, just about all the problems that we work through in this section will have some substitution quality to them, right? Most of them will be some kind of u substitution going on. And the guidelines we use, kind of this odd power of sine process that I'm thinking about here, will take advantage of those substitution techniques. So all I've got left to do then is to kind of distribute here. This is like the integral of u to the 6th minus u to the 4th, and antiderive each one of those terms. And I've got u to the 7th over 7 minus u to the 5th over 5, and then replace u with cosine x. So I've got cosine to the 7th over 7 minus cosine to the 5th over 5 plus c. Okay. And there's my antiderivative. So the techniques here in this section are, like I said, largely based on substitution, right? That's kind of the background of everything going on. But just about all of them are going to require some sort of identity usage. Okay? Let's do another. The integral of cosine cubed x divided by the square root of sine x dx. So this one might be a little bit easier, a little bit tricky, depending on how comfortable you are with substitution. For the most part, we try to let a u, if we're going to substitute, be what's under the radical, right? And that's really no different in this case. If u is sine x, then du is cosine x dx. And I've got a cosine x in the numerator. In fact, I've got 3 of them. If I take one of them away, then I have an even power left over, okay? And that's a very useful thing. So what I'm going to do here, I see cosine x dx is up there. I've just got extra powers. So similar to the last problem, I've got an odd power of cosine. I'm going to pull off a factor of cosine so that it can take the place of my du, right? Du is cosine x dx, so I can replace all that underlined portion there, what I've pulled off, with du. And u then will just be my sine. So what I've got in the numerator then is a cosine squared x. That cosine squared I can replace by 1 minus sine squared. And since u is sine, I can replace it with 1 minus u squared. So in the numerator, 1 minus u squared. I just do a complete substitution, and I use the powers of sine and cosine to my advantage. I pull off a factor of cosine in this case, and that's pretty much because cosine had an odd power originally, and I can take everything else and replace it with sines, because that's what I made u. Okay? From here, I just simplify the powers of u. All right, so this is u to the minus a half minus u to the positive 1/2. Antiderive each one of those, add 1 to the power, divide by the new power, and I get 2u to the 1/2 minus 2/3 u to the 3/2 plus a constant. Replace u with sine of x, and I've got 2 square root of sine x minus 2/3 sine x, and I forgot the power 3/2. Okay, that's it. That's all there is to it. Again, another substitution. The next example is a little trickier, and it's in a way just because it's simpler. But what I've got here, sine squared of theta d theta. I've got an even power of sine. Okay? If I were to replace this sine squared with 1 minus cosine squared, use that Pythagorean identity, what I see is that my integral now has 2 terms in it. I can now split this integral apart into the integral of d theta minus the integral of cosine squared theta d theta. The first one, this guy here, d theta, I can integrate that, right? That should just give me a theta. Minus integral of cosine squared. I started with the integral of sine squared, and I'm no better off here. Right, I've got another cosine squared. I would have to kind of repeat my process, right? I'd have to replace cosine squared with 1 minus sine squared, and maybe that'll yield me something. It's tough to say. There is a better way. The other formula that we had on the previous page, or on the beginning slide, was this power reducing identity. So it says it's sine squared of theta was 1 minus cosine of 2 theta, all divided by 2. Okay? And in terms of integration, this is a nice thing because I've just got cosine of a linear angle, right? I've got cosine of 2 theta, and that's something I can integrate really pretty easily. I'll show you. So I replace sine squared of theta with 1 minus cosine of 2 theta divided by 2, and I wrote it a little differently here. I pulled off a factor of a half, because when I integrate, I can just move that constant outside of my integral. Okay? And then I can think about this like two separate integrals here. Integral of d theta minus the integral of cosine of 2 theta d theta. And I write it like this for a reason, because to integrate cosine of 2 theta, you might substitute. You might take 2 theta out, and then du would be 2 d theta. You could use a substitution here, but that substitution would be a little confusing if I were to do it in this previous integral here. It would kind of mess things up. We can kind of work our way around that substitution. What derivative would I take to get cosine of 2 theta? Well, it's got to be sine of 2 theta, but derivative of sine of 2 theta would be a 1/2 cosine of 2 theta. I don't have a 1/2, so that means I've got to multiply this guy by a 2. So what I should end up with is a 1/2 theta minus 1/2 sine of 2 theta plus c. In fact, I said multiply by 2, I meant divide by 2. It would give me an extra factor of 2 if I were to take a derivative, and that factor of 2 I want to cancel, I want to get rid of. So that's why we see this 1/2 out here. That's from my substitution. All is done here pretty much. I just want to show you the other form. Distribute that 1/2. It doesn't matter. We're done. We've integrated that sine squared of theta. If I were to have an integral of cosine squared theta, I would do the same thing. Same idea. I would use my power reducing identity and reduce that down. Okay. Now for some guidelines here. These guidelines are going to pertain to evaluating integrals with sines and cosines. I can kind of generalize this in some kind of general integral like sine to the n times cosine to the m, all with x's in there, dx. Okay. So there's kind of 3 different situations that are going to come up here. Yes, you could potentially think of more, but the main 3 that we're tackling in this section are as follows. The first one, we say that if sine has an odd power, if n is odd and positive, what we do is we break off a factor or a power of sine and convert everything else, the remaining factors, to cosines. Okay, so then I've got multiple powers of cosines, I've got one factor of sine broken off, and everything else then should be converted to cosines. The reason I'll do this is because I would let u be cosine, then du would be minus sine something, right? I just write those in general because I don't necessarily just have x's. I might have something else. I might have sine of 2x or something in the argument. So I'm leaving those a little generic. But then that factor of sine that we pulled off will take the place of my substitution when I take that little derivative du, okay? That's the first strategy when n is odd and positive, when sine is odd and positive. The next is with cosine, and it's almost the exact same, just backwards. If m is odd and positive, so I've got an odd positive power of cosine, we break off a factor of cosine and convert the remaining factors to sines. Okay, convert the remaining factors to sines. In this case, we would let u be sine and du be cosine. Okay? Those work together rather nicely, and we're taking advantage of the relationship between the derivatives of sine and cosine there. Okay. The third and final guideline is the one I showed you in the previous example. If n and m are both positive and even, if I've got even powers of sine and cosine, I make repeated use of those power reducing identities. Okay? Those situations can be cumbersome, especially as the power increases, right? If I've got sine or cosine to the 4th or 6th, those just are, like I said, cumbersome. They take a little while to do. There's a lot of algebra going on that you'll work with. I just wanted to show you kind of a basic one with sine squared or cosine squared, but all of those even powers of sine and cosine fall under that same category, okay? Practice plenty of these. There's no way I can show you every single possibility, and that's why these are called guidelines, not rules, right? So sometimes another method might work. You might be able to just substitute some other way, or wiggle things around so that the integration is easy without having to follow the guidelines here. But they're kind of a nice, quick way to be able to evaluate integrals with powers of sines and cosines. In the next video, we'll look at powers of secants and tangents and just a few examples there. Thanks for watching.